seen the people standing on the shore. I seen a big chief there standing on the shore. I asked my mama.
Okay, onwards to chapter 4. And we're going to start with a chapter where we're going to do over 2 days. And you've already done a lot of it, so that's good news. It's called 4.1, Increasing and Decreasing Functions. So the first thing we're going to do is introduce this very, very important concept in mathematics. Do it a lot in Foundations 12. It's called sets. And a set is a collection of distinguishable items. So you could have a set of many, many different sorts of things. So one example would be the set of all the students taking Calculus 12 this year. And then I would list all of your guys' names. Another possible set would be all of the teachers in King George, and I would list all of the teachers in King George, obviously. But in math, oftentimes what you're talking about with sets, you're talking about different sorts of numbers, and that's what we're going to be looking at in this particular lesson. So we're going to be looking at intervals a lot. You've looked at these before. Intervals are sets of real numbers that correspond geometrically to line segments, and I have the word "to" written twice there. I'm not sure why. So this might not sound familiar, but you know this. There's open intervals and there's closed intervals. An open interval is all numbers between a and b excluding the endpoints. It doesn't include the endpoints. By the way, the endpoints would be a and b. A and b. So there's two ways you could write this. You could say a comma b with circular brackets like this, and that means from a to b, but not including a and b, everything between those two numbers, right? And the other way you could do it is you could write it like this. A is less than, let's call it x, which is less than b, and you're familiar with this. But now we're going to put it in proper set notation, because this is the way they do this in your work, in your textbook. This is the way you'll probably have to do it when you get to university, is you actually designate a set, and the way you do that is with curly brackets. So I know this is very difficult for some of you, but you're going to put curly brackets around here, and then you put the letter x, just like you have there, the same letter. If this was a y, you'd put y there. If it was m, you'd put m there, and then you put a vertical line. Now, what does this mean? This means, actually going to write it, this means the set x such that dot dot dot. So basically what this is saying then is the set x such that a is less than all the things in this set, and all the things in this set are less than b. It's really just exactly the same meaning as it always has been, but we have this little extra piece in it here, the vertical line and the curly brackets, to show that we're talking about set theory. Okay, now another thing I know you're familiar with is how to graph this. What you do is you make a very, very small number line, you put on the numbers a and b, and you decide for yourself, am I going to put open circles or closed circles? Well, since this is an open interval, you're going to put open circles, open points, open dots, and then you connect them. You can connect them like this, but the way that I prefer to do it, as some of my students showed me years ago, is you do it like this. It's easier to read. Okay, so that's an open interval. A closed interval is just like this. It's all the numbers between a and b, but includes the endpoints, which again, if you want to include it there, the endpoints are a and b. So how would that look? Very similar to this. It would be a comma b, but they'd be square brackets. In terms of set theory, you would still say the set x such that a is less than or equal to x, which is less than or equal to b. And the way you graph that, you'd put a and b, but you would put closed dots before you connect them. Okay, there's two other possibilities. What if all the values we're interested in are less than a, or all the values we're interested in are greater than b? In that case, we have an infinite interval. So an infinite interval goes towards positive infinity or towards negative infinity. Okay, now there's many different infinite intervals, right? You could go from a certain point a all the way up to infinity, and it might include an a. It might include a, so you put a square bracket. Infinity, always a circular bracket, because you can never get to infinity. It could be an infinite interval from a to infinity, but it doesn't include a. It could be an infinite interval from negative infinity up to a, or b, to any letter you want here, Again, always circular around the infinity, and let's say it does include a, or it could be from negative infinity up to a, and it doesn't include a. So these are 4 different possibilities. The way you would write them, gosh, this is going to be kind of a mess here, but the way you'd write them in the other form, the set theory form, okay, for this one, it's from a to infinity. So what that means is we're looking at the set x such that x is greater than or equal to a. Second one, we have the set x such that x is greater than a, but not equal to a. Next one, we'd have the set x such that x is less than or equal to a. And the fourth one, we have the set x such that x is less than a, but not equal to a. Now, I don't want to do the drawings, the graphs for each one of them, so maybe I'll just do the graph for, I don't know, the last one here. So what we have is just one point necessary, a, and we want to have a open circle at a because it doesn't include a, and it's going down towards negative infinity, so you do it this way. Of course, for this one, you'd fill in the dot. For this one, you'd have open dot and it would face to the right, and for this one, you'd have closed dot facing to the right. Okay, what we're going to do now is go from one form to the other. So from like the purple form to the red form. So if we have this one from -4 not inclusive to 7 inclusive, how would we write that in set theory? Well, what you would say is we're talking about the set x. This is always going to be the case, although it could be a different letter, but we'll just stick with x. And we're going from -4 less than all the x's, not inclusive, so that's it, and which is less than or equal to 7, and then close your set. The way you would graph that, of course, is you'd put those two numbers, the -4 and the 7. What kind of dots you need? Well, in the -4 you need an open dot, on the 7 you need a closed dot, and it goes between them. Okay, from negative infinity to 11. So we have the set x such that all the x's are what? They're all less than 11, or including 11. So they go down to negative infinity, so they're less than 11 or also including 11 because of that square bracket. And close the set there. How do you graph that? Only have to put one number on it this time, which is 11. What kind of dot do you need? You need a closed dot, and it's going to go to the left. Okay, now we're going to go the opposite way. It's actually a bad example because I haven't written these in set theory, which I've just been teaching you about here, set theory. So it's pretty bad. If you want to do it in set theory, put your curly bracket, x such that x is greater than -3, close it. Same with this. Curly bracket, x such that -8 is less than x, which is less than or equal to -3, close it. Anyway, you should be able to do it whether you have it in the set theory or not. So in this one, x is greater than -3. How are we going to write that in interval notation, which is with the brackets? Well, the only number we have listed here is -3, and all the values are bigger than that. So that means it would be from -3 up to infinity. It doesn't include -3, so I have a circular bracket, and it never includes infinity, so I have another circular bracket. How do I graph that? Only have to put one number, -3. What kind of point? Open, because it's a circular bracket here, and it goes up towards infinity. Okay, the other one, it goes from -8 to -3, so I can put both of those numbers. Let's figure out the brackets. Not including -8, circular. Does include -3, square bracket. Let's graph that. So we'll put our two numbers, -8, -3. Kind of dot would be circular on the -8, square dot on the -3, and join them together. There you go. Okay, now we're going to solve some inequalities. Okay, this first question here is a linear inequality. You know it's linear because there's no x squared or cubed or anything, so this is a linear inequality. The way you're going to solve that is the same as you would just solve regular equalities. You just have to remember one special rule, and that is that you're going to flip the inequality sign if you multiply or divide by a negative, right? So I'm going to say flip sign if divide, because it's almost always divide by a negative. Besides that, you just do the same steps you normally would do. Okay, so let's solve that. I guess I'd move the -2x over, so I'd have 2 is greater than 12 plus 5x. That'd become a positive 2x when it moves over. Then I'd subtract 12 from both sides, so I get -10 is greater than 5x. Divide both sides by 5. I get -2 is greater than x. Now, if you want to write the x first, remember it's -2 is bigger than x, or x is less than -2. That's our answer. You could graph it if you want, but we won't bother doing that. Of course, the other way you could write that is you could say if x is less than -2, that it goes from -infinity all the way up to -2, but it doesn't include either one. So this is also a good answer. Okay, the second one here, this is a quadratic inequality. The reason it's quadratic, of course, is because of that x squared. Now, the way to solve those, there's different ways to do it. The way I like to do it is to temporarily make it equals. So we would have x squared minus x minus 30 equals 0. You know how to solve quadratic equalities. You make it equal to 0. Hey, we already have it equal to 0. And we try to factor. And you can factor this. You have x minus 6, x plus 5 equals 0, which means x equals 6, and x equals -5. Now, are those your answers? No, because we're looking for all the values that are less than or equal. We found the ones that are equal. We still need the ones that are less than. So what I like to do at this point is I like to make something that's called well, it's not called this at all, actually. It's called a wiggle graph. Now, it's not called that at all. I found this in some book. Here's the awful thing. There's two awful things. One, it's a really goofy name, wiggle graph. The other thing is I can't really remember why it's called a wiggle graph. It doesn't really make sense to me anymore. I know that's pathetic, but I just can't remember. I'm sorry. So I'll see if I can figure it out as I do this. Anyway, the way you do a wiggle graph is you make a very small number line, you put these points on it, put them in the right order, so I'd have to have -5 here and 6 here, and then you're going to test points in all of these different sections. Now, I know in the past you've done something like this and we only tested one section and then alternated, and that will work with quadratics, but just please this year get in the habit of checking every single section. So where do you check it? Well, it makes sense to check it right here. You could also, and it might actually be easier to check it here in the factored form, as long as you realize it's not actually equals, it's less than or equals. So either one of those two that you want. I'll show you why the factored one's nice in a second. So let's pick a point bigger than 6. How about 10? I don't know, it can be 6.1 if you want, but I'm going to pick something easy. I'm going to try 10. So I'd put in here, I'd get 10 squared, which is 100, minus 10, which is 90, take away 30, which is 60. Is 60 less than 0? No, it's not. So this section did not work. Let's try, what would be a good number to put in here? 0. 0 squared, 0, take away 0, 0, take away 30 is -30. Is -30 less than or equal to 0? Yes, it is, so this is a check. How about this one over here? How about -10 this time? -10 squared is 100. Take away -10, you're up to 110. Take away 30, it's 80. Definitely doesn't work. So there you go, you now have your answer. Why is it nice to use the factored form? Because then you don't even have to worry about the actual numbers, right? When I was doing 10 squared and getting 100 and everything, all you really have to worry about is positive and negative. It's pretty awesome. So for example, if I was going to do up here and I was going to use 10, you just go 10 minus 6, well that's positive. 10 plus 5, well that's positive. Positive times a positive? It's positive. So positive is definitely not less than 0. So I know this one didn't work. Let's try another one. Let's try 0. 0 take away 6, that's negative. 0 plus 5, that's positive. Negative and positive is negative. Yep, negative or less than 0. So using the factored form is probably the best way to do it, and that's probably what I'll do from now on. Okay, we have our answer now. We can graph it. What we found is it goes from -5 up to 6. Now, what kind of bracket should we put on that? We look back up in the original, and it was less than or equal, which means we have to put our square brackets. Of course, you could also write this as -5 is less than or equal to x, which is less than or equal to 6. Or you could even do it in set notation and put x such that, and close the set. So there you go. Any one of those are fine. Okay, let's do another one of these. So this is not linear, so we're going to have to do our temporary, at least this is the way I do it. There are other people who do it differently, but I like doing the temporary rewriting of this where we make it equal to 0. And then we're going to try to factor. Now careful, you can factor this by taking out a greatest common factor of x, which leaves you with x squared minus 6x plus 8 equals 0. Then try factor the trinomial. You'll get x minus 4 and x minus 2 equals 0, which means our answers are, don't forget this one, x equals 0, x equals 4, x equals positive 2. So these are the numbers that I'm going to put on my number line. 0, 2, 4. 4. And I'm going to use the factored one in this case. Remember that our sign is less than or equal to 0, and I'm looking right here. So let's do some test points. Let's start by doing up here. How about 5? If I put 5 in here, I get positive. 5 minus 4 is positive. 5 minus 2 is positive. 3 positives multiplied together make a positive, and positive is not less than 0, so this one up here did not work. Okay, let's try between 2 and 4. Let's try 3. 3 is positive. 3 minus 4, well, that's negative. 3 minus 2, that's positive. We only have one negative. It was positive, negative, positive. That makes the whole thing negative, and negative is definitely less than 0, so this works. Let's try 1 in between 0 and 2. 1, that's positive. 1 minus 4, negative. 1 minus 2, negative. Positive times a negative. That's two negatives make a positive, so it's the whole thing's positive, and positives aren't less than 0. This one doesn't work. And let's try something down here. I don't know, let's try negative 60. It doesn't matter. It's so easy if you do it this way. Negative 60, that's negative. Negative 60 take away another 4, it's definitely negative. Negative 60 take away 2, definitely negative. Negative times negative equals negative, and negatives are less than 0, so this works. Okay, now we have two regions that work. We have this region down here, and we have this region down up here. So we're going to use set notation to write this. How do we do it? First thing we have to do is figure out what kind of brackets we're going to use. Well, it's less than or equal to, so if you want, you might even want to get in the habit of putting the points on here right away. When you wrote the 0, the 2, and the 4, you might have wanted to, and I think I'll start doing this from now on, might have wanted to say, hey, wait, since it's less than or equal to, I know that these are all going to be solid dots here. And it turned out the ones that worked, if you want to even do this one worked, and this one worked. So we have to represent both of those regions. How do we do that? Well, this region down here, this is from negative infinity up to 0. Of course, we always put circular on the negative infinity, and it includes 0. And then from this one, it was from 2 to 4, and it includes both of them. Now, what should I write in between them? Well, some people like to put and in there, but that's not correct because there's no number that's in this region and this region. So you can put or, but if you want to use very nice set notation, what you do is you put this U, looks like that. And this means union. Union means elements belong to one set or both. Okay, last one, and this one's a little bit trickier because it's a rational inequality. Okay, it's quadratic, and it's also rational. So when you're doing these rational ones, the ones with fractions, you have to be careful. You have to find the zeros, like we've been doing here, right? When we found the 0, the 4, and the 2, those are the zeros. You have to find the zeros, and you have to find the NPVs, the non-permissible values. You have to put them all on your number line here. So let's do that right now. So because it is quadratic, we're going to make it equal to 0. And why don't we find the NPV right now? The NPV of this is whatever makes the denominator equal 0. Well, that would be negative 4. Now we're going to solve that. We can get rid of the denominator now because you could multiply both sides by x plus 4. If you multiply this side by x plus 4, it cancels. You multiply this side by x plus 4, you're just left with 0 still. So all we have left is x squared minus 3x equals 0. Let's factor by taking out an x. So you get x times x minus 3 equals 0. We can find our zeros, which are 0 and 3. So let's be careful here. What numbers are we putting on our number line? Yes, we are definitely going to put 0 and 3, but we are also going to put negative 4 on there. Why don't we right now decide what kind of dots we're going to put? You want closed dots or open dots? Closed dots again, because it can be equal to. So I'll put some closed dots on here. Now we're going to test out the sections here. So how you might actually want to test it out is in factored form, this x times x minus 3, but include the denominator that we'd started with at x plus 4, and it's less than or equal to 0. So this is where I'm going to test it in here. So let's do that right now. And again, all you need to do is worry about positive and negatives. So something bigger than 3. Let's try 5. If I put 5 in here, I get positive. 5 minus 3 is positive, and 5 plus 4 is positive. So positive times a positive divided by a positive is definitely positive. Positives are not less than 0. This did not work. Okay, let's try between 0 and 3. I'll try 1. 1 is positive, 1 minus 3 is negative, 1 plus 4 is positive. Positive times a negative divided by a positive, it's all negative, and that works. We want it to be less than 0. Okay, let's try negative 2, I guess. Negative 2, so that's negative. Negative 2 take away 3, that's also negative. Negative 2 plus 4, that becomes positive. So we have negative, negative divided by positive. 2 negatives make a positive. Basically, the whole thing's positive. This doesn't work. And the last one, we have, let's try negative 10. Negative 10, well, that's negative. Negative 10 take away 3, that's negative. Negative 10 plus 4, that's negative. They're all negative. Negative times a negative divided by a negative, it's going to be negative. Hey, that works. So our regions that work are here and here. So it's actually very similar to the one that we just did. We're going to end up having from negative infinity up to negative 4 inclusive, and then the union 0 to 3. So or from 0 to 3. And there you go. That's your answer. Okay, thanks everyone.
Always there.